Suppose this is the free body diagram of this body. Now just pay attention. Now, what are the various forces acting on this body? We can say that we are giving the motion in this direction. So in this direction we have the velocity, in this direction we have the velocity, and also in this direction we have acceleration. X double dot is acceleration. In this direction we are giving the displacement, so acceleration will be in this direction. And if you push this body in this direction with the distance of x meter, then this spring will stretch by the x meter. So this spring will exert a force on this body in this direction. A force will be applied by this spring on this body in this direction, and that force will be equal to its stiffness into the distance by which it will be expanding, the stretch or the expansion of the spring, x, right? Because they are fixed at this point. So if this mass is moving in this direction by x unit, so the spring will be stretched by x unit, so the force acting in this unit in this direction will be x. So this will be the free body diagram of this mass. Free body diagram of this mass. Now we will solve this question with the help of two approach. I will explain all of them, two approach, one by one, right? First of all, we'll solve this with the help of Newtonian approach, Newton's motion, right? First of all, we will solve this with the help of Newton's law. So first is here, we will apply Newton's second law. Newton's second law. Just pay attention. What the Newton's second law will say that? Newton's second law says that the net force in the direction of motion will be equal to the mass into acceleration of this body. This is the Newton's second law. Newton's second law says that the net force in the direction of motion, will be equal to mass into acceleration, or you can say inertia force, right? Inertia force is mass into acceleration. That is the Newton's second law. So if I apply this, so in this case the inertia force is the mass of the body into acceleration x double dot. So this inertia force will be equal to the net force in this direction. What is the net force in this direction? The net force, if we are talking about in this direction, the net force is minus of kx, because this spring force will be acting in this direction. So in this direction, the net force in this direction will be equal to minus of kx, right? We are taking in the opposite direction. So this will be equal to minus of kx. So from here I can write that mx double dot plus k into x will be equal to 0. This is the basic equation of motion for your free vibration when the body will be in translation. This body is in translation. So this will be the this is the basic equation of motion. So in this case, this can be written as x double dot plus k by m into x will be equal to 0, right? This is your second order differential equation, right? This is your second order differential equation. So if this is the basic equation, then we can say that this parameter under root of k by m, this will be equal to your omega n, that is your natural or angular frequency of this system. This is your angular frequency, right? In the vibration question, you always need to find what will be the angular frequency of the system. So the angular frequency will be equal to under root k by m. Under root k by m. What is the k? K is the coefficient of x, m is the coefficient of x double dot, right? You just read always note what I am saying. This is under root k by m. K is, this numerator is the coefficient of this x term, m is the coefficient of this x double dot, right? So this is your Newton's second law. This is from your Newton's second law. But in our case, in our general conditions, we always prefer the another law, right? While solving the question of your vibration, we always prefer the second approach, that is your Lambert's principle. The second one is your Lambert's principle. This Lambert's principle you study in your mechanics, right? Lambert's law you studied, so we'll not go in detail. We will say that what is the Lambert's principle? Lambert's principle says that suppose this is this block, this is your block. So let us say on this block the net force will be like this. On this block the net force will be in this direction, that will be equal to kx. Lambert's principle, on an overview I am saying, Lambert's principle says that in the direction of net force, if you add your inertia force, then the summation of these two will be 0, right? In the direction of the net force, I am again saying, in the direction of the net force, if you add the inertia force, then the total summation will be equal to 0. So in the direction of net force will be in this direction. So in this direction, if I add this inertia force, then the net force will be equal to 0. So we can say that mx double dot plus kx will be equal to 0. The same equation which we get from the Newton's second law. The same equation which we get from the Newton's second law. You have to remember this generalized equation of the free vibration, that is mx double dot plus kx will be equal to 0. Mx double dot plus kx will be equal to 0, and in this case also the angular frequency or the natural frequency, this is also known as your natural frequency. Sorry, natural frequency is different. This is your angular frequency, and that will be equal to under root k by m. Under root k by m. From the Lambert's principle or from the Newton's second law, the results will be the same, right? So this is the case when the motion is your linear motion. The motion is your linear motion. Suppose in the case when the motion is your rotational motion. Suppose we have to discuss the case when the motion is your rotational motion. For example, if I say, for example, suppose we have a disc here, right? Let us say we have a disc here, and this disc is attached with a torsional spring. This disc is attached with a torsional spring. So this is your torsional spring. This is your torsional spring whose stiffness is, I am denoting with k theta. For the torsional I am writing k theta, right? Now suppose this is in its equilibrium position, and now suppose the moment of inertia of this disc is I. I is the moment of inertia of this disc, and let us say for this disc, after achieving its equilibrium position, now if I disturb the equilibrium position of this disc, if I give this disc a slight rotation in this direction with a angle theta, right? With the angle theta, if I rotate this disc like this, if I rotate this disc like this with an angle theta, and if I leave it, then it will be in this to and fro periodic motion, right? This will be the vibration. So what will be the equation in this case? We can say that in this case is, what is the, you can see the motion is in this direction. The motion is in this direction. So the acceleration, that is theta double dot, will be in this direction. So what will be the inertia force in the direction of motion? The inertia force is your I into theta double dot. I into theta double dot is the inertia force in the direction of motion. Now if you give this disc a angle theta, then this torsional spring will also deflect with the angle theta. It will give you a restoring force in the opposite direction. So we can say that this spring this spring will exert a force in the opposite direction, and that will be equal to its stiffness into its rotation, k theta into theta, right? So this is in the opposite direction, but from the Newton's second law, you know that from the Newton's second law, the net force in the direction of motion will be equal to your inertia force, or if you apply the Lambert's principle, you will also get that in this direction, in the direction of net force, if I add I theta double dot in this direction only, then the total summation will be equal to 0. So from the Newton's second law, you will get here, from the Newton's second law, you will get this will be equal to minus of k theta into theta double dot. This is from the Newton's second law, and if you take it from here, so this is I theta double dot plus k theta into theta will be equal to 0. So this is the generalized basic equation of free vibration when the system is under rotation. When the system is under rotation, and in this case the angular frequency will be equal to, this omega n will be equal to, if you remember in the translation case, we will write this is under root of k. K is the coefficient of x. Here we have theta, so k theta, right? The coefficient of theta is k theta divided by the coefficient of theta double dot, that is I. That is I. So this is your angular frequency of this disk. This is the angular frequency of this disk. So you will find the angular frequency like this, right? So this is the case when the system is under rotation. Now suppose we have another case. Let us take a case of pendulum, right? We'll take all the cases here only, so that there should not be any confusion. Suppose we'll take a case of pendulum. Let us say we have a pendulum here. And this is a pendulum ball. Right. Now, suppose we can say that, suppose the mass of this pendulum ball is m. It is hinged at this point. It is hinged at this point, let us say, and the length of this string is L, and this string is massless. I am assuming this string is massless. This string is massless, right? So if I disturb this equilibrium position with an angle theta, if I disturb the angular position, if I disturb the equilibrium position of this ball with an angle theta, suppose this is your rotation of angle theta, and now the ball will reach here. Let us say the ball will reach here. Now just pay attention. What we did, we are giving some angle theta to this pendulum in this direction. In this direction we are giving some theta, and we left it. Now what will happen? This ball will be under vibration. This pendulum will be under vibration, and this is the equilibrium position of the vibration of this pendulum. This is the equilibrium position. Now what will happen? Suppose this is angle theta. Now what is the force acting on this ball? The force acting on this ball will be in the downward direction. The force will be your gravity, that is the weight of this ball. Weight of this ball will be acting in this direction, right? Now what is the perpendicular distance? If I take the, because this is under rotation, so we have to balance the torque, right? Now suppose what is this perpendicular distance? If you remember from your basic understanding, what is this perpendicular distance of this force from this angle of rotation, this point of rotation, right? This pendulum is rotating about this point. So what is this distance? If this is L, this length is L, this length is L, so this distance will be L sine theta. This distance is your L sine theta, right? This distance is your L sine theta. This length is L, so this upon this will be sine theta, so this length will be L sine theta. And if I say that sine theta will be approximately written as, this will be equal to theta if theta is small. We know this from the basic mathematics. if your angle theta is small, then we can write sine theta will be equal to theta. So this length will be equal to L theta. This length will be equal to L theta. Now what is the torque acting on this at this point because of this weight? What is the torque acting? So in this direction, right, this is the mg into L theta. This is a torque acting in this direction about this point O, about this point O. So what is the torque acting? That is your mg is the force into L theta is the distance, perpendicular distance. So this is the torque acting in this direction. This is the only force acting in this direction. So now I will solve all the question from the Lambert's principle. I can say that in the net direction of motion, in the net direction of the force, if I add in this direction, if I add the inertia force, then summation of these two will be 0. The summation of these two will be 0. Right, in this direction only I add. So I can say that from here, I can say that I theta double dot plus mg into L theta will be equal to 0. Right, now what is the moment of inertia of this ball about this point? That is ml square. The moment of inertia of this m about this point is, this is length L, this is ml square. We know, right? This is acting as a point mass, and this string is massless. So I will be equal to ml square. So I can write ml square theta double dot plus mgl theta will be equal to 0. From here I can say that m and m will cancel, L and this L will cancel. So from here I get L theta double dot plus g theta will be equal to 0. So this is the basic equation of this motion. This is the basic equation of this motion, and from here I can easily calculate what is the angular frequency. That will be equal to under root, what is this? K by m. K is the coefficient of theta, that is g, divided by coefficient of theta double dot, that is L. So this is the angular frequency of this system. This is the angular frequency of this system. Right, simple. I'm not doing anything, I'm just denoting the torque in this direction because this is under pure rotation. So in this direction, if I add inertia force, the summation of them will be 0. So this is the angular frequency in this case. Right.